In this last session here, we'll be hearing from startups about their experiences as well as from shared facilities that have enabled their journey. My name is Jorg Scholvin. I am with MIT.nano, and I'm delighted to moderate the next two sessions or parts of the sessions. I've actually seen portions of the journeys that we'll hear about from both directions. One as a researcher launching an SBIR-funded company based on my postdoctoral work, and then over the last 4 years through involvement in managing the Fab at MIT.nano as the Assistant Director for User Services. So in this session, we'll get a chance to first learn from 3 startups about their journeys. And in the second part, we'll learn from managers of shared facilities who are often central at enabling the early development of startups. So we'll hear from each speaker now. After 10 minutes of presentation, we'll have a few minutes for questions from the audience. So feel free to type that into the chat and we'll try to get to as many as possible. And with that, it's my pleasure to introduce our first speaker. Veronika Stelmakh is the CEO and co-founder of Mesodyne, an MIT spinout that is commercializing a new class of power generator to convert fuel into electricity through light. And they are achieving over 10 times the energy density of lithium-ion batteries. Veronika holds a BS in electrical engineering from the University of Texas at Arlington and an MS and PhD in electrical engineering from MIT. Veronika.
Great. Thank you for the introduction, Jorg, and thank you for having me. I'm the CEO of Mesodyne, as you mentioned, and we are building a new kind of power generator. So the problem with power today is really that there's no reliable, long endurance, portable power solution available. But from unmanned drones and vehicles to sensors in remote locations to dismounted warfighters, our need for this kind of distributed, reliable power demand is ever increasing. And the solutions that we have today are primarily batteries, which are, of course, very common because of their portability and cost, but they have very low energy density, which means that they don't last long and they need to be recharged. So on the other hand, internal combustion engines, they have very high energy density, but as you reduce their size, they will lose their efficiency. And they're also very loud and they require constant maintenance. So fuel cells have been developed to try to bridge the gap between batteries and internal combustion engines, but they require specialized fuel, which significantly impacts logistics. And they also have potentially reliability issues. And then, of course, solar and other alternative energy sources can be great, but they are not necessarily reliable because they depend on the sun or the wind. So there's really no adequate, lightweight, long endurance, reliable solution available today. And that's what we're working on at Mesodyne. We're building a new kind of power generator that we call the light cell to enable efficient, reliable, quiet, portable power anywhere, anytime, and from any fuel. And the way that it works is that we have a new way of converting any fuel to electricity via light. So it's a multi-step process. First, we generate the heat by burning fuel in a small microcombustor, and then the heat brings a photonic crystal selective emitter to incandescence, and then the resulting radiation drives low band gap photovoltaic cells to generate the electricity. And in 2017, my co-founder Walker Chen and I, we demonstrated the world record efficiency for this type of energy conversion, which is called thermophotovoltaics. And we patented this technology during our PhD at MIT. So our light cell generator has a number of advantages over current solutions. Primarily, the main advantage is that it has extremely high energy density. And so you can increase the endurance of drones or other small systems up to 10 times over batteries alone. And the light cell has no moving parts, which means that it's reliable, quiet operation with no vibration, unlike, say, internal combustion engines. And the way that we burn the fuel is different as well. The microcombustor heats up to more than 1,000 degrees C, which results in a complete combustion of the fuel. So this means that this is a cleaner operation, no smell, no smoke, no particulates. And we can run on most commercial and military fuels, unlike fuel cells, which are restricted to just one type of fuel. And finally, the solution is modular from about 50 watts to 5 kilowatts, depending on our customers' needs. There are, of course, many applications for this kind of generator in military, industrial, and commercial markets, but we are initially focused on products for military applications. This is where the pain point is really high, and there is a higher willingness to pay as well. So the 3 products that we're currently working on are a smaller man-portable power generator, a larger stationary power generator, and a larger drone range extender. And the value proposition, again, is 10 times the flight time, or essentially 10 times the endurance for the soldier power, which also actually results in a 70% weight reduction when compared to the number of batteries they would have to carry to achieve the same amount of energy on a 72-hour mission or longer. So we have received primarily non-dilutive grants to fund this technology to transition from the lab to the product demonstration, though we did we have a contract with a large defense contractor now, and so we are demonstrating that product currently in one of their systems. But it took a lot of government grants to get to that point, and actually a lot of early stage programs and resources. So we started out at MIT, and we participated in a number of MIT entrepreneurship competitions and accelerator programs. So probably Delta V at the Martin Trust Center was the biggest one. And then VMS had the Translational Fellows Program, which is now the MIT I-Core node. And both of these programs really helped us understand customer discovery, how to have a business really, and led us to participate in actually the NSF National I-Core program, which then enabled us to get our first SBIR grant, which of course, that's once you receive your first grant, you can actually open an office or hire officially an employee. So that was really a huge pivotal moment for us. Another pivotal moment was our participation in DOE's Chain Reaction Innovations program at Argonne National Lab, which is a sister program of the Activate program that you just heard about. And that program was, of course, transformational because it enabled me to work full-time at Mesodyne with the resources of a national lab while, getting traction and applying for grants and hiring more employees. That led us to actually also participate in the Air Force Techstars and Mass Challenge programs, which were extremely helpful to get more funding specifically from the Air Force and understanding the Air Force pain points. And so now, right now, we have 3 phase 2s that we're actually working on with the Air Force. And finally, we participated in the Army's X-Tech Search, which helped us understand the Army's value proposition. And we participated in NextCore's Luminate program, which was really helpful for how do we scale beyond the academic clean rooms? What kind of partnerships do we need to have to build particularly the photonic crystal aspect of our generator? But our main challenge today is actually cost reduction, because cost reduction is the key to unlock revenue. And to get to cost reduction, you need volume, and to get to volume, you need traction with your customers. But to get traction with your customers, you need a product. And if your product is really expensive, you can't get there. And so this chicken and egg problem is really why we need programs, especially for hard tech, deep tech, startups that enable us to build things with limited resources. And especially in our case, the light cell has 3 key components, the microcombustor, the photonic crystal, the PV cell, and then the rest of the system. But really the photonic crystal and the PV cells, these are specialized components that you can't just buy off the shelf or can't even really outsource yet, because they have to be fabricated by us essentially in the clean room. And so the photonic crystal, that's the key a component that enables our efficient energy conversion because it reshapes the radiation that's coming out of the microcombustor to something that can be efficiently converted by the PV cell. You need a multi-million-dollar facility if you're going to build your own to fabricate this, relatively simple photonic crystal, which is manufactured with standard semiconductor manufacturing processes. It's just an array of holes in a wafer, but the wafer is metallic, so it's not a silicon process. So that basically limits 90% or maybe more of all the facilities we can use because we're not doing a traditional silicon wafer manufacturing. With the PV cells, if you wanted to manufacture the PV cells yourself, you would also need a multi-million-dollar facility because these are not standard silicon photovoltaic cells. These are cells that are using different 3,5 compounds, and of course, this is very difficult to manufacture just in your garage. And so those are, in my opinion, the critical barriers to innovation right now in the semiconductor industry, or in generally speaking, for startups that require a clean room, is that, you need that cost reduction. It's critical. But in order to get there, you need to have a more standard process. You can't work with contract clean rooms because they have their own quotas to meet, and they want to have a low risk process that's not going to ruin their process. And then of course you can't build a clean room facility because that requires a major capital investment. And so it's really critical to have access to shared clean room facilities. And at Mesodyne, we're building our key components at MIT.nano, Harvard, and we actually also started a collaboration with SUNY. And so without these facilities, we wouldn't be able to be where we're at today. So I'm really excited that this is something that is being looked at, and I'm looking forward to seeing more access to resources for companies like Mesodyne.
All right. Wonderful. Thank you, Veronika, for an inspiring presentation. Let me open it up for questions, and perhaps start with in prototyping your technology in a shared facility. Could you tell us what worked and what didn't? Because often you're required to adhere to sort of the academic standards in the lab, and perhaps it's not as industrial as you would prefer. And then perhaps also what's next? How do you bridge to the next level of fabrication and mass production?
Yes. So the first question, the challenge with the academic clean rooms, the access to the tools, when you're a student, you obviously have access through MIT, for example, but being able to participate in a program like Start.nano is really critical because just the cost difference to be able to operate at lower cost, it enables us to be able to prototype things that are, difficult to prototype. But also, I guess one of the challenges too is that our requirements are a little bit different from an academic environment. We need a more repeatable process, a larger scale process. And so having access to the different tools and being able to iterate is really critical. I mentioned this earlier too. We're not using silicon, and that is pretty much a deal breaker for most facilities other than academic facilities, because we have to bring this non-silicon wafer into the fab. And so being able to do that has really enabled us to build our company and build this product. What's next is that, in order for us to convince a bigger facility to manufacture this kind of device, for example, the photonic crystal, we need to have that fully mapped out, using standard tools, and demonstrate to them that, this is a viable process. And so really the only place you can do that is in an academic clean room, which is what we're doing now.
I see. Great. So in some sense, you mentioned that the metal as a material, as opposed to standard silicon, in order to scale up to a bigger facility to go into mass production, is it then mostly a question of proving to those facilities that you're compatible with their workflows, and perhaps more of a question of time and money, or are there sort of fundamental limits that would prevent you from running it in a traditional fab?
I think it's to demonstrate the compatibility because there's no precedent. So to show that, well, if it's working, in this clean room with all these other processes, it would work in your clean room as well. So I really think it's a compatibility issue, and that no one else is really introducing those kinds of materials in those facilities.
Right. Okay, great. Maybe one last question. You mentioned a couple of programs, but perhaps what facilities and programs were particularly important to accomplish your success? And maybe as your company changes, which ones of those programs will still be needed as you go to the next level in the next stage of your company?
Well, I think the ones I highlighted were really critical, but specifically for a hardware kind of, deep tech startup programs like the DOE's, chain reaction or activate. I don't think that there's anything else like that provides that kind of support at an early stage where you really still need to demonstrate the technical feasibility. A lot of programs focus, I think, later on when you have your prototype, how do you test that and validate it with your customers. But there are a few that really support the initial R&D phase, and I think that that's really critical. And I think we could use more of those programs that enable access to those kinds of resources, like these really expensive multi-million-dollar facilities that you did have access to as a student, but technically now as a startup, you don't have access to.
Got it. Awesome. That's a great insight. Let me thank you for the wonderful presentation. And we're going to move on to our next speaker. Our next speaker is Nate Cady, the Empire Innovation Professor of Nanobiosciences at SUNY Polytechnic Institute in New York. His research focuses on the development of novel biosensor technologies and biology-inspired nanoelectronics, including novel hardware for neuromorphic computing. He's also the executive director of the SUNY Applied Materials Research Institute that funds collaborative research efforts between SUNY faculty and the industry partner Applied Materials. Nate.
Jorg, thank you for the introduction. So as Jorg mentioned, I'm at SUNY Polytechnic Institute, which is in Albany, New York. And today I want to tell you a little bit about the interface between the startup side of the world, the academic side that I'm on, and then the foundry or fabrication facility that we have here on site, which is the Albany Nanotech Consortium here in Albany, New York, which is really kind of a co-run facility between New York Creates and SUNY Polytechnic Institute. And what it is a semiconductor fab facility that's capable of 300 millimeter wafer processing. We have a complete silicon line straight through from advanced lithography, including your typical optical, E-beam, and EUV type of tool sets for litho, all the standard deposition and etch processes. We do packaging here on site and at some partner facilities in New York State. We do full CMOS processing on a few different nodes, as well as a lot of what we call short loop and derivative development. So basically taking portions of the full CMOS build and running those out as literally short loops of a few components of the stack. And derivative development would mean bringing in new materials or new devices into the normal silicon process flow for CMOS that would be different than what you would normally run. We're also home to AIM Photonics, which is part of the American Institute for Manufacturing, focused on doing integrated photonics on wafer, with lots of good collaborations with other universities and other partners across the country. For design enablement in-house, we do have available for partners a full design kit for an older CMOS node, 65 nanometer, 10 LPE, which is licensed from Global Foundries. and then full PDK for silicon photonics. And then for advanced nodes, we run all the way down to some of the very most advanced silicon technologies, not necessarily the full flow from front end to back end of the line, but certain portions of those nodes that we run here. So we're kind of a funny institution because we're this silicon foundry that's surrounded by the academic side, which I'm on, as well as all of our industry partners that are here on site, either as an equipment supplier or as a company that's actually in the business of building chips. And where do startups fit in with that? One of the easiest ways for startups to become connected is through their interactions with professors like me. So I end up interacting with companies through SBIR and STTR projects where I'm the academic component of that, but I'm also the gateway to the fab for being able to do fabrication of individual devices or actually delivering full CMOS for that project. And so it's a funny niche to be in, but it's actually a great entry point, and it'll lead me to my last slide eventually, where I have some thought on how we can do that better. So here's a typical type of development pipeline. We have maybe new materials and devices that someone wants to demonstrate, and so I list a number of these here. We can then demonstrate fabrication with what I mentioned is a kind of a short loop process where we bring in just a certain stage of the technology. So for example, I do a lot of work with resistive memory devices, and we can focus on just the back end part of the stack of CMOS where we want to integrate those materials and devices without necessarily needing all of the overhead circuitry to do proof of concept. Eventually, we can work with partners to do full integration and then packaging, and then work with other partners here on site to really go full scale. And so that may be actually sending companies or partners offsite here to a traditional foundry, but we can work with our on-site partners here to have their process ready to go and be accepted. And of course, we work with all of the other various funding agencies and various places where we hope that these technologies go. So I'll give you three kind of quick case studies of how we've kind of served as that bridge between startup companies and then their ability to manufacture either a prototype or actually a very small volume of product for their company. So the first case is CNC Incorporated. We started working with them mainly on trying to transfer a technology they had for building optical grating structures for a surface plasma on resonant technique from a different fab into our fabrication facility here, from a glass-based process to a silicon-based process. And so it included a lot of etch development and development of the litho process, as well as our own quality control that we could run in-house to test those gratings and make them acceptable for this industry partner. So the first steps are really to develop a litho flow and actually produce these grating structures across full 300 millimeter wafers. So you see here stitched die across the entire wafer. These are gratings with 250 nanometer lines and spaces across the entire wafer. We then had to develop a kind of a unique etch process. Most reactive ion etch type of processes that you would run for nearly any process would be an anisotropic etch with nice vertical sidewalls. We actually had to go backwards for these gratings to try to get this sinusoidal type of pattern. So a lot of etch development in the fab to change what would be a standard process to something that would yield the structure we were looking for. And then later, we had to come up with a procedure for getting these wafers out of the main 300 millimeter fab and into our accessory, more of a user type of facility where we could deposit materials that weren't allowed in the fab. And so that includes the gold optical layer that's on the surface of these chips that give it their plasmonic properties. So that was another kind of part of the development process. So where did this end up? Multiple patents have come out of this, multiple journal articles. And then we're now a kind of a small volume supplier for Ciencia for these grating structures. And now we've been helping them to transition from a silicon-based technology to other approaches to making these gratings in higher volume. So the next couple of examples I'll give you really leverage the technology that we had already developed in-house. So this is work that my group has done on integrating resistive memory devices with CMOS. So these are also sometimes known as memristor devices, and they act like a synapse in your brain. So basically, you can form a better or worse connection between two electrodes through a filament formation process. They're a non-volatile memory, so they hold their state when you remove power. And they're actually very nicely vertically integrated with your standard transistor flow. So we took our 65 nanometer CMOS process here in the line, added a couple of levels in our back-end process, and we're able to integrate these resistive memory devices in what we call sort of a middle of the line flow, or very early back end of the line process flow. So we were using these in my group anyway, and had developed this process, making memory arrays and doing some interesting work in the neuromorphic computing field. And we started connecting with a few companies who had a similar need for this type of device. So one was Sparrow Devices, who was basically looking for a pathway towards manufacturing in a foundry. So they really needed to be able to do demonstration of what they were proposing in both software and hardware in a potential resistive memory platform that could be transitioned to a standard foundry. So we were able to take our memory arrays that we were developing, do yield and reliability testing that was basically necessary to try to transition a process to a foundry, and then include some custom circuit design, where we leveraged some other funding programs that we were doing projects under to do basically what we call multiple project wafer runs. So this is where we aggregate lots of different designs into one big design, and then run that as an entire run. And each customer or each rider gets their little chiplets that come off of the full wafer build. So this project was a success in that it pushed us beyond our limits for reliability and yield testing, and also gave Sparrow the data they needed to both move forward with a proof of concept of what they were doing from more of an algorithm perspective, but also get closer to be able to bring this technology towards production and foundry. The second company that we're working with right now is Xilinx, and so Xilinx started up out of Cornell University as a spinoff, and they're doing basically custom hardware for wafer probing. So a very interesting MEMS type of approach for being able to probe structures and devices on wafer. And what they were really looking for was someone to be able to do proof of concept testing, both on the electrical test side of things, but also a partner to potentially develop a higher volume or a larger volume production of their probers that they're building. So what we've been able to do so far with Xilinx is basically do custom designs of our CMOS and hardware, including much smaller size probe pads for them to be able to demonstrate efficacy of their system, but also start working with them to figure out how to transition their base MEMS type process to a larger scale. I would call it kind of pre-foundry testing here at our site at SUNY Polytechnic, Albany Nanotech environment. So out of these case studies, what's the outlook, or what are the lessons learned? Well, from my own work and then working with several of these companies, what works well is being able to take an existing process flow. So for instance, this hybrid CMOS and resistive memory flow that we have developed, and be able to transition that towards either delivering that technology directly to our partner so they can do proof of concept, or having a very clear pathway towards transition to manufacturing. The short loop processes that I mentioned work very well. This is not something you'll find at a normal foundry, where you can only use a thin slice of the process technology to basically demonstrate your material or your device in just part of the flow. Multiple project wafer runs work really well to offset the overall cost of masks, the reticles for doing patterning, plus all of the development work. What's challenging is providing design services. So everybody has their unique or licensed process design kit and design software. And so, as Veronika mentioned, with a small startup, you can't necessarily afford to obviously build your own fab, but you often can't even afford to buy the latest and greatest design software needed. So how do we better support, especially startup companies with those design services or getting into that design pipeline? Another problem is underestimating the amount of development time that you need to get a process up and running. It's a huge challenge if you bring in a new material or a completely different process flow, and expecting that a fab will just turn that around and change all their processes and get you yield on your wafers in a very short amount of time is unrealistic. So you need to make sure there's enough time built in to get those processes going. It's expensive to buy reticles for the litho part of the work, and it's also expensive to do that process development. So making sure there's a clear picture of those costs, and then figure out how to offset them with things like multiple project wafers is important. The last thing here in the challenges is flexibility is an issue. Even in our fab, which is more of a research fab, we still have a lot of restrictions because it is a CMOS base flow that runs through that line. And now with the addition of silicon photonics on top of that, there's a lot of process limitations. And so it is a challenge to bring in a brand new material or kind of a crazy left field process without convincing a lot of people that it's not going to break all their tools or poison their wafers or devices downstream. So I think is needed. I think if we're thinking in the context of a nationwide initiative to bridge these gaps, we need to provide better design enablement or design services and access to IP, such as process design kits, to help facilitate, first of all, getting designs up and running. I think we need more multiple project wafer type of access, whether that's full CMOS or running shorter loops where but be able to have these demo platforms that are not as expensive to run for the riders that want to buy in is important. The other thing I would mention is we need to do a better job mapping existing process technologies at the lab scale. So this is any of the user facilities across the country in the network where people are doing their initial proof of concept on small wafers or different processes. How do those map to a fab like here in Albany, and then again from there to an actual foundry? And so I think if we do those mapping studies, we'll know the right way to send people through the network and actually get them to be more successful in transitioning their technology towards actual production. That's all I have. Thank you very much for the opportunity.
All right, wonderful. Thanks, Nate, for an excellent presentation. Let me open up for questions and maybe start with one. How does a startup access the SUNY Albany space, and maybe what are the selection criteria, or what's the selection process for that?
Sure. So we're not a user facility like Cornell and I think MIT.nano, where you would sign up to be a user and then mainly process wafers yourself, maybe with some help from staff. You either can access us through a faculty engagement. So as faculty here at SUNY Poly, we have access to the line and can help with basically connecting to the fab and getting processes going. Or you can go directly through New York Creates. So New York Creates is the entity that really runs the fab facility. And so they can engage at a company to fab connection point to discuss getting a process up and running. So either of those are valid and good ways to get into our facility.
I see. So those, either New York Create or the faculty, act as kind of the owner of that process, or the in between the startup and the actual fab.
Yeah, that's the connection point. And then we have a full-time staff of engineers on the fab side of the house who, once you've made that connection, can look through your process or look through what you want to do and figure out if we already have a flow for that or what would be needed to get that up and running, right, as well as costing and everything else.
Okay. Something maybe somewhat related. Is there perhaps something of the companies that you've mentioned that utilize SUNY Albany, plus other companies that run wafers there? Is there something that those startups have in common, perhaps in terms of their technology needs or their technology readiness level?
Yeah, we're mainly a silicon fab. There's lots of derivative technologies that are starting to be run through the fab here. And I mentioned that we also have silicon photonics now in addition to the normal CMOS. So the common factor is typically most people have engaged through electronics and now photonics applications. What we don't see quite as much of, but I think is a good way to leverage a fab like this, is what I call either the short loops, or you just need a few levels of deposition, patterning, etch to define structures. And so we see less of that, but I think it's a good way to fairly quickly run wafers through at low cost and be able to demonstrate some level, or to be able to make a substrate that then you use in a different fab to build up from. So for instance, very large arrays of very small structures that we can do a better job patterning, but you can do a better job with your unique material at your own home foundry or home fabrication facility.
Imagine if people run that on 300 millimeter wafers, but have access to a smaller academic fab, how would they bring those wafers back?
Yeah, so we have kind of two answers to that. So we do a lot of work where we process a full wafer, but then send out coupons. Those can't come back. Full wafers typically can't come back unless they comply with all of our contamination protocols for coming back in. We have sent out from this line to a foundry line and then back. And so there's iterations there where you might be able to go between foundries. And this may be an exercise in the future to find out how other user-based facilities might be able to do that back and forth, so we could actually do a round robin with wafers. That might be a really exciting way to think about the future.
All right, awesome. Perhaps one last question. The 300 millimeter tools are relatively expensive, and running those tools is also cost can be quite high. How do startups typically cover those costs? Are there discounts or programs or other ideas to help them?
Yeah, the way I think about our facility, it's a full line. So you're not paying on a per tool usage type of basis. Really, what you're paying for when you come in here is access to the line, and you're paying for overall processing. And so it's a little different than the user facility approach. This is why I mentioned, though, the multiple project wafer approach or joint and having access to those types of flows, because the biggest expense would be actually buying a full reticle set. So if you wanted to do a full end-to-end design, that's your huge ticket item before you even get into the fab at all. Needless to say, also you have to pay for all the development costs for the process. But I guess just the perspective is think about it more like you're accessing a line rather than individual tools.
Right. Awesome. Well, thank you so much. That's excellent. And our third speaker is Remus Nicolaescu. Remus is the co-founder and CEO of Pointcloud, a San Francisco-based startup that's developing coherent 3D imaging solutions using silicon photonics. In 2017, together with a team at University of Southampton, he co-founded Pointcloud to create a versatile, integrated, three-dimensional imaging chipset that would enable 3D cameras to become as ubiquitous as their 2D counterparts. Remus.
Well, thank you, Jorg. Thank you for the introduction, and thank you for the organizers for inviting us and to present the company as well as our perspectives. So I will start with a little bit of an overview of the company. I will try to keep it short as the topic of the workshop is a little bit different, and then I'm going to transition a little bit into our manufacturing strategy. And from there, a few perspectives of challenges we encounter along the 5-year journey of the company, as well as a few ideas that might look a little bit, maybe a little bit of a Santa Claus list, but I thought I should just throw them out there and at least as a starting point. So starting with the company, as it was already mentioned in the introduction, we developed a chipset. The way you think about it, it's essentially sort of the analogous of the image sensor you have in your regular camera, except that instead of producing 2D images, it would produce point clouds. And the point cloud is something that would look like this simulation that is on my screen here. So the founding team is essentially, there are 3 of us. It's Professor Graham Reed at University of Southampton. He's been in the silicon photonics world for a long time. He's one of the pioneers of the field started about 30 years ago. Dave Thompson, who was his student at University of Surrey, and then he became a professor himself at Southampton. And myself, my background, I started back at Intel 20 years ago when silicon photonics started at Intel. As I was mentioning, the way to think about our product is really the equivalent of the CMOS image sensor in the 3-dimensional world. And this is an actual sort of a sketch of how the chip looks like. You can think of it as a focal plane array of pixels, except that just like you have in your camera with a lens in front of it, except that each pixel, instead of detecting charges and accumulating charging and measuring those, it's a coherent detector. So it detects an analog signal. Now we pair this with a frequency modulation approach, and what we essentially measured is the frequency of a bit node that we receive from the target. And actually what you're seeing here, the animation, is the way the sensor illuminates the target. So we essentially send the beam through each pixel of the array and scan the entire target area, and then the light scatters back into the pixel where we measure the bit node. So the advantage of combining frequency modulation CW with a solid-state focal plane array approach is that you get the best of both worlds. You get a performance that is characteristics of frequency modulation systems, very high resolution, very good range. We fundamentally have single photon detection, accuracy, and we also get the fourth from the 4D, essentially radial velocity measurement. The integrated approach, the focal plane approach, brings us the simplicity and the versatility of the system. So we have essentially a single chip, a single lens. There are no alignment steps. It works fundamentally as far as imaging exactly the same as a regular camera. We've actually made these devices. On the left side, you have the picture of the chip. It's a 16 by 16 pixel demonstrator. It is fully integrated, not only just the optics, but here we integrate all the electronics. It has all the amplification stages on the chip. It also has all the electronics for switching, for even the digital to analog converter. So it's truly a single chip 3D imager. And the only thing that we're feeding into that is a laser signal. And also next to it is going to be a signal processor to take the signals coming out of the chip and extract the frequency. In the middle, you have a measured point cloud. So it actually works very, very nicely. It's already, we're doing actually, this is a 50-meter range point cloud. It's one of the exercise balls in the office. We have very high energy efficiency, millimeter class accuracy, and as I mentioned before, simplicity. Now shifting a little bit into a little bit of a background about the company and then going into the manufacturing strategy. So the company was started in San Francisco, and we always had also a presence in Southampton. We work pretty closely with a team in the Optical Research Center at University of Southampton. And we're actually currently we're opening a new subsidiary in Zurich in Switzerland, and we'll be ramping up activities on the design side there as well. As far as front-end manufacturing strategy, from the very beginning, we realized that one of the biggest problems we're going to have is it's essentially time to volume. And so while it took quite a bit of effort to be able to get access to a tier one commercial foundry, we eventually managed to do so. So we essentially designed pretty much everything on that is more like customer facing on the silicon photonics. In the past, we've designed it on the silicon photonics 90WG process at Global Foundries. Together with this, and I think actually Nate was mentioning that he would encourage people to do these short loops. We do use the fabs at the clean room at University of Southampton for short loops, for select components development, as well as for occasionally to do tests of different concepts. So this is not necessarily customer facing, it's more like for our own learning purposes. Also in the future, it's not only front end that we like to work, we try the best we can to work with commercial at scale manufacturers, but also on the back end. We've done most of the packaging development also with large facilities that essentially once it moves from the development stage in the R&D labs, it just moves across the street in a large volume facility so we can ramp up quickly. This is a little bit of a timeline of how this looked like. We've actually done 5 tapeouts in these, I would say actually 3 years, because the last 2 years were pretty much, we struggled through the pandemic, so it was a little bit of a slower period. We did 3 of them at Southampton, as I mentioned. It was 2-axis solid state steering. This was the first demonstration, like very basic demonstration of a switch. Then we did a couple of modulators there, as well as a proof of concept of backside illuminated architecture. So we just showed that you could potentially do a backside architecture. The 2 things that actually were customer facing were both done in Global Foundries. So the first one was the bistatic system, and this is the full system with transmitter, receiver, steering, everything on the same chip. And then the second test chip was included a monostatic architecture, which you've just seen on the previous page. we have actually published the bistatic architecture was the topic of a Nature paper published at the beginning of 2021. So now shifting a little bit away from us as a company, so shifting a little bit on the perspectives as they relate to our journey through the last 5 years. So first one, I already sort of touched base a little bit on manufacturing. While it looks like it was a success, it sort of hides a little bit the difficulties that we had, and I would actually say that it was a combination of some pretty hard work, some relationships, because we're all a little bit more older, so we're not coming out straight out of the university, so we knew a few people, a lot of very, very nice, kind people that actually were willing to take a chance on us, and quite a bit of luck to be able to have access to and to become direct customers of a large tier one. As I mentioned, university clean rooms are great for development, though the problem with it is that if you start to develop a device that needs to go in the market, you pretty much have to restart from scratch once you have to go to volume, because you have no path to volume production. And most of the time, the foundries material stack as well as DRC design rules decks are very different from what a transition fab or a clean room, university clean room would have. The second problem that we see is there were different words used here. It's like, I think I've heard the valley of death, or we call it no man's land between sort of basic research, which essentially is what you're doing in a university, and then market fundable commercial product. And typically, people will want to see to get market funding some sort of viable commercial product that the customer would be willing to buy. In a university, you generally do basic physics demonstrations and that sort of thing. And we're a little bit of a weird creature because we did some of the basic physics demonstration at the very beginning. So we kind of had to struggle a little bit with the fact that we hit a period when it was actually very, very hard to find both customers as well as VCs that were willing to talk to us for the next round. The next one is ecosystem expertise gap, and this is something that, again, like we've seen sort of in our experience. It's by default, when you are at the leading edge of something, you are the one that knows it best from everyone out there. On top of that, our customers are not experts in how to make our devices; they're experts in how to use our devices, which doesn't necessarily bring them insight into, is this feasible? Is it actually possible to make? And on top of that, VCs typically go to your customers to ask to see whether you have market traction. So they rely on the customers to evaluate your technology. So both these links are, you essentially, if none of them understand what you're doing, it becomes really, really hard to actually get any traction. So on top of that, what we also had was that we were using telecom technology, so silicon photonics that was developed for telecom, for an imaging application. So we had people that understood imaging and people that understood silicon photonics. We actually never found people that understood both of them. So that became also a little bit of a difficulty as far as convincing people. Finally, the last bit is on funding. And to a certain extent, both development gap and ecosystem expertise gap are also related to funding, because you can get your next money to be able to develop the next stage. And I actually think that there is also a mismatch in profile, because if you look, and I actually pulled this data from our attorneys, which run a quarterly survey. If you look at the median, you see a 3 million median for a seed stage, you see a 5 million roughly median for a seed A and for a Series A, and you see a 15 million for a Series B. And this is also, your VCs will expect to see customer traction before A. And this is something that might work for software because it's relatively easy to build something and start to get a few customers. But for a semiconductor company, you essentially need to build a product first. And for that, you need a lot more money. You typically need in the $10 to $15 million range. You can do a proof of concept, a very simple little device on an MPW, but you can't actually do something that a customer will be convinced that, okay, I'll buy this. So we typically need a bigger A, and also we don't have customer sales pre-A. A few ideas on manufacturing. One thought was to try to incentivize foundries to, I mean, to a certain extent, maybe put some money into large manufacturing facilities to attract them in the US, but also maybe link it to those foundries providing even a small amount of capacity to like small players and companies that are trying to develop things. Even like if it's like 1% for a foundry like a tier 1 foundry, it's essentially nothing. And I think that would be also the advantage of the foundries, because at the end of the day, foundries want new applications to fill their fabs. The second one is, and I'm actually kind of seeing some of this, and I think it was mentioned also in Nate's presentation, try to align a little bit the material stacks and the RC rules with the design rule kits with potentially a larger scale foundry. That would make life a lot easier. At that point, you can actually use a transitional fab or I don't know, maybe university fab is a little bit difficult, but to do that. But and it's an example, at least what they're pitching to us, and I'm not sure, we haven't used them yet. CA-Leti, for example, of the silicon photonics process, claims that their DRC rules are identical with a ST process. Therefore, you could design things and make them in CA-Leti, and then without a lot of pain and suffering, you might be able to move them into a large scale fab. Development cycle gap. I don't think there is any magic solution here. It really comes down to the fact that the time cycles are very long. I was actually going through some of the history, and at Intel, it took us like 15 years to more or less get to the silicon photonics process developed. At IBM, I was looking for some of Vlasov's early presentations. I think I saw things from like 10 years ago that were already starting to come out, but I'm assuming there were another 10 years before then at IBM Research. So you're looking at 15 to 20 years horizons with massive amounts of funding. So I don't think there is any magic solution other than, I don't know, national fabs, public-private partnerships, some serious funding from the government. Ecosystem expertise gap here, I think it would be, I don't know how feasible this is, but maybe to have some sort of a more formal pool of academic and industry experts that market participants can consult. I could sort of give a little bit of an anecdote. I was actually thinking through our pitching process. I think we pitched probably to over like 100 funds. And I think there were exactly 2 that brought a knowledgeable scientist that understood what we were doing in the meetings. So they tried all sorts of other things. They tried to call customers. They tried all sorts of things, but credible people that actually understood our technology, there were 2. I could say that there was a third one, possibly, sort of. But that's kind of the level. Finally, funding gap. I saw here that Veronika had a lot more funding from the government. For us, we're not a military application. We typically target very, very large volume consumer, so mobile, AR, automotive. We looked for a little bit, and maybe we just didn't spend enough time, but it didn't seem like there was anything that was fitting us either on DARPA or any other of the other programs. So I think sort of it would be nice to have some funding also for civilian applications, not just for the military. And finally, maybe more simplified and less rigid frameworks. The other thing that we noticed when we were looking for, we looked a little bit also in the UK to apply together with our partners, and the process was really very complicated. So it was very different from our VC materials. So it was kind of hard we would have had to essentially have a full-time person just applying for grants, which we ended up deciding not. It's just too much risk and not enough reward. So we ended up not trying to. Finalizing, we're hiring. So if on this call there are any silicon photonics, optics, mixed signal, RF system engineers, we're especially hiring mostly in our European locations. We would love to hear from you. Thank you.
All right. Well, thank you for a terrific presentation. I want to just briefly, perhaps one observation and a question. It was quite fascinating to see that parallel use of academic and industry fabs at the same time. How do you bridge that or port the work over what goes on in the university clean room to global foundries, especially with the different equipment and different wafer sizes that come into play?
We actually don't. So the only things that we did in Southampton were things that never needed to get ported. So, for example, we did the first demonstration of a switch. A switch, a two-dimensional switch, is like a bunch of 2x2 Mach Zehnders. So it's something that we just wanted to show our investors, look, there is an easy way to do two-dimensional switching, and here it is. And it was a simple process, very few steps, just a few metal steps, just a few etches, and we ran it in 2.5 months, 3 months, and it was out, and we had the demonstrator, and we can say, okay, this is done, it can be done, we're going to do it now in global foundries. The second one, we demonstrated backside illumination, and it was the same thing, where they just did something on which we use a metal layer to reflect light back to the backside of the wafer. Again, just a proof of concept showing that this works, there are no problems. Now we can try to move this concept into the main chips.
Awesome, wonderful. Well, thank you so much, everybody, for participating. It's been really insightful, and I want to actually highlight one question that was here on the chat that we didn't quite get to, and that is, from a student who asked, these technologies are very impressive, orders of magnitude improvements and things that didn't exist before. But how do you know how to start on that journey and put the time and effort in, particularly in technology and hard tech, where it'll take a lot longer to prove that your idea is valid or not. So I don't know if there's any parting thoughts on that from the three of you.
Okay, should I go? And
any order is good.
To be 100% honest, when we started, and this was back in 2017. Right now, there are more people doing what we're doing, and I suggested to Graham, like, hey, how do you feel like about putting 500,000 silicon photonics components on a chip? We had no idea whether it's going to work. That's as simple as that. We had no idea whether this is going to work. It actually worked way beyond our wildest expectations. Mm-hmm. So I think the short answer is, I don't think you always know that.
How long did it take you to figure that out, I guess?
That it worked? Or?
Yeah. So from the idea to kind of knowing that it was feasible.
I would actually credit this to global foundries. And this is one of the huge advantages of working with a commercial tier one foundry. I had some of the guys that my team came out of Stanford, and they were like, we've never been in a place that things just work the first time. It's like, that is the advantage. You design according to the design rules. We were very strict. We never asked for waivers. Everything was DRC clean when you went to the foundry, and what you get back is what you designed. Mm-hmm. And so I don't know. I'll credit global foundries for this one.
Awesome. I think Veronika, you were same question to you. Yeah.
Well, I think for us, we were both my co-founder and I. We were students at MIT, and we had that publication, which was, a really exciting result. And I think at the time we were maybe a little naive. We thought, oh, this is a really great result, and someone needs to take this to the next level. And if not us, then who? Because, there's not that many people doing this. In fact, we were one of the few groups in the world, working on this. And so for us, it was just a natural transition to try to commercialize this technology. We definitely didn't, I think we underestimated the amount of time and resources needed. But once you're in it, it's like, you're, it's such an exciting journey. And, we're so thankful that we've been able to get here. And I guess, we wouldn't really be here without the government grants in our case because of the timeline. And but I guess to address the question, yes, you don't know if it's going to succeed or not. But if you are excited about it and you have the drive, then I think you can take it to a really exciting new place. And I think as a scientist, I've always been excited to push the boundaries of some field, and that's what we are able to do. And I don't think I would be able to do that in any other company than Mesodyne.
Awesome, wonderful. We're actually a couple of minutes behind, so we're going to move on to our next panel. I'll exit this room and reemerge in the other place. But thank you so much for taking the time and talking to us and enlightening us here on your journeys and everything. So thank you so much.
Thank you.
Thank you for having us.